Morning, everyone, or shall I rather say, good afternoon, DevConf Cape Town. I hope you are all having a wonderful time, and don't worry, I know that there have been many good speakers thus far today, but luckily for you, the best is yet to come in like it's me, sorry, I'm the, spoiler alert. A while ago, I embarked on a journey. This was a journey that had the potential to affect the rest of my life. We've all had moments like these in our lives. A job interview that needs to go well, a fiancé, hopefully, that needs to say yes, or our first piece of code that makes it into production, that needs to not kill a bank. In many ways, my journey was very similar to these. It was my degree. I was in the final year of my computer engineering studies, and the only thing standing between me and a shiny new degree, or at least a nicely printed piece of paper, was my final year project. Now, this project stood in front of me like an absolute mountain. Never before had I had such an important event in my life. And to make matters worse, or at least more stressful, I had the absolute privilege of being given a bursary by a fantastic software engineering company that I was very excited to join. Can you just imagine the phone call that I'd have to make if I didn't pass, and just sort of how that phone call would go? Yes, hello, BBD. Yeah, so I won't be joining you. Why? Well, I'm enjoying my studies so much that I want to do them for another year. Luckily for me, I only failed 2 modules during my studies, and my argument is always that I just enjoyed them so much that I wanted to do them again for a second time. From a young age, I've always loved building things. My dad is a mechanical engineer, and together we've taken apart everything from cars to kettles. It's from him that I learned the value of voltage and current after accidentally connecting a 12-volt receiver to the 230 volts of our house and having it explode with such force that it proceeded to break the light hanging above our heads, which then came crashing down at our feet. So, when the project selections came around, I knew I wanted a project where I could use my hands to build something. One thing led to another, and the end of a rather long story is that I ended up needing to build a handwriting robot. A robot capable of replicating the handwriting of a human. Now, I asked AI what a robot like this should look like, and this is what I got. Luckily for me, I have been blessed with terrible handwriting. Bad enough where I even contemplated becoming a doctor just so that I would fit in. Handwriting so bad that not even a paleographer would be able to understand it. Now, for those of you not versed in the realm of scriptural exegesis, a paleographer is someone who decrypts and deciphers ancient handwriting to understand historical documents and manuscripts. Basically, my point is, my handwriting is super bad. This, combined with the threat of future joblessness, inspired me to tackle my project head-on. Hi, my name is Stefan Jager, and luckily I never had to make that awkward phone call, because after successfully completing my project, I graduated from the University of Pretoria with a degree in computer engineering and joined BBD as a software engineer. Through the journey of building my robot, I had many struggles that I had to overcome, many challenges that I had to face, and many lessons that I had to learn. I would like to take you through this journey and share some of those lessons today. Where should we start? Well, where any good story starts, at the beginning. First principles, specifically in engineering, means starting from the most basic facts and building up from there. First principles are to engineering concepts what grassroots are to political concepts. They are heavily emphasized throughout engineering and are a strict requirement of all final year projects. Many of us would have learnt about first principles, whether it's in our job or our studies, and they honestly suck. But let me not get ahead of myself just yet. To build a handwriting robot, you need to start at the end. Now, the fancy engineering phrase for this is top-down design, bottom-up implementation. So, starting at the top, what is everything we want this robot or system to be able to do? Now, for us, that's simple. The robot needs to replicate the handwriting of a human. Once we understand the end goal, we can start to sort of split things up. So, let's split things up. Well, since it's a robot that needs to do handwriting, we would naturally need a pen. So, let's start there. Now, a pen is great, but it can't really do anything unless you move it, right? It's sort of like a bicycle without pedals. You might look cool standing next to it, but you're not really going anywhere without a little help. So, how do we move this pen? What do we know in our world that can move things? A car. Cars move stuff. Buses move people. That seems fine. Ooh, what about an elevator? They move things all the time, right? Up and down all day long. What about another person? Now, I would like to ask my lovely, pretty assistant to please write down your name and your favorite color while a room of 200 people stare at you with increasing intensity. Whatever you want.
Don't judge.
We are all judging together. Ladies and gentlemen, I present to you Handwriting Robot version 1. It's voice activated. You just have to pay some salary and give it food every now and then. And beer. Okay, maybe we need to bring our sort of ideas maybe slightly more realistic and maybe narrow down our search. Do we have any existing technology that's similar to what we want to achieve? 3D printers. FDM 3D printers can accurately control the movement of their nozzles to print in high detail. This is perfect. Okay, let's build a 3D printer. How do we do that? So a 3D printer can move its nozzle up and down, and there are many ways to achieve this, but luckily for us, we only want to move a pen, and so up and down can sort of be thought of as like a Boolean, where we are either touching the paper or we are not touching the paper. 3D printers can also move their nozzles left and right, and they do this by using bearings that glide on rails and all fancy things like that to achieve this. Okay, we now have some system to move our pen, but it's like a car without an engine, so let's add some engines. Or to be more accurate, let's add some motors. Since we want to accurately control the movement of our pen, I'm going to opt for some stepper motors. Now, stepper motors are great because unlike traditional motors that just spin around and around, by carefully controlling the voltage on each of their input wires, you can get a stepper motor to turn an incredibly small distance and stop, 0.9 degrees to be exact. How do I know this? Well, trust me, I'm an engineer, and also it says it on the side of the motor. It's through these incredibly small distances that we can accurately control the rotation of the motor and in turn accurately control the movement of the pen. We now have all the parts that would allow for movement. Our pen can be moved up and down. It's nicely sitting on some rails with some bearings to move left and right, but we have nothing to control the actual movement. So let's write some code. Believe it or not, but even something as complicated as this can even use an Arduino. For those of you who don't know what an Arduino is, it's like a very small, very powerful, but very stupid computer. It has these pins on it called GPIO, or General Purpose Input-Output pins. Using some very basic code, we can get it to turn these pins on and off. Doing this, we can control the motors and get them to move how and when we want them to. Behold our robot. We have a pen, we have stuff to move the pen, and we have stuff to control the stuff that moves the pen. We now have a pen that can, in theory, move, but I mean, pen movement is just one small step required in writing. We still need to figure out how to capture human handwriting in a way that the robot can understand and write it. My solution to this problem came from a projector. How many of you, well, I guess from where you're sitting, you see smooth lines. But from where I am, real up close to the screen, I see pixels, many tiny little squares that all come together to create some image. Let's use that as a base for controlling our pen. This image looks normal and natural, but it's made up of many tiny little squares. There are actually no smooth lines anywhere here. What if we use this as a base? What if, given an image, we find a black pixel, move the pen to that point, and just dot on each little black pixel? That way we can write some image. Okay, let's do that. Let's build a system that takes an image, which is just a 2D grid of squares. We move the pen, we have something that looks for a black pixel. We move the pen to that point. We then dot and lift the pen and repeat the process until we've dotted on each black pixel. This works great, but it results in something that looks far from actual human handwriting. This is because humans write by keeping their pen on the page and finishing a letter. So maybe lifting the pen the whole time wasn't the best idea. Maybe we should try to bring our implementation closer to what humans do and sort of keep the pen on the page for longer. We can achieve this by following a special procedure. Given an image, find a black pixel, move the pen to that point, put the pen down. We then look around the pixel for any neighboring black pixels. If we find one, move the pen to that point. Look, move, look, move, look, move, look, move. We continue this until there are no more neighboring black pixels that we haven't drawn on already. Then, and only then, do we lift the pen and look for another black pixel, or until we've drawn the whole image. Now, the slide explaining all of that would have been super cool, and it would have had an animation, and it would have made so much more sense, I promise, but sadly my PowerPoint skills are as bad as my handwriting. If we put all these pieces together, we end up with a robot that can draw or write some image. If it's an image of a house, we can draw a house. If it's an image of someone's handwriting, we can write that too. But I know what you're thinking. What does this have to do with writing the handwriting of a human? I mean, all that we can do is just copy some picture. Well, this is where the magic of cameras comes in. To start the process, we first need a picture of someone's handwriting. For this demonstration, I have a sample of this person's handwriting. For those of you who might not know who this person is, her name is Candice Mesk, and she is one of the hosts of DevConf. And I thought that she would be the perfect person to use for this demonstration, for reasons that we will see later. Once we have a picture of the handwriting, we need to get it into a form that we can use to make our own sentences. Now, or we need to get it into a form that we can write it. So the images that we take of handwriting technically are full of color. Some spots might be a little bit brown, others slightly red, and there are a lot of shades of gray. We don't want that. We want the white of the paper and the black of the pen. So we need to binarize the image, meaning that any sort of black pixel gets converted to black, and any sort of white pixel gets converted to white. That way we end up with an image that's made up of only two different pixel values, black and white, with nothing in between. Like any typical client, on any typical project, I'm now going to throw a metaphorical spanner into the metaphorical works and slightly clarify the goal of our system. Earlier, I explained that the system needs to replicate the handwriting of a human. Now, sadly, this isn't as easy as just copying what they've already written down. Instead, the system actually needs to produce new pieces of handwriting in the handwriting of a human. Like many of you here, when I got this slight requirement change to my project, my first thought was, what? You want me to do what? How? I then had to take a nice long sit down for the sake of my own mental health and sanity and think about this new problem in front of me. How is it possible to take someone's handwriting and write something completely new that they've never written before. I mean, to do that, I'd need to teach the robot how someone's handwriting looks. I'd need to be able to then build custom sentences based off of those handwriting, and then, okay, but wait, at that point, the handwriting is just a picture, and we already know that our system can draw pictures. Okay, new goal. Let's build a system that creates templates of how each person writes their letters. That way we can take those templates and put them together in any order to make any sentence that we want. Well, the first thing we need to do is get a sample of how each person writes their letters. The quick brown fox jumps over the lazy dog is a great sentence since it uses each letter of the English alphabet. If we can have someone write the sentence out, once in lowercase and once in all caps, we then have a sample of how that person writes each of their letters. Okay, let's try that again. I now have my quick brown fox in Candace's handwriting, and we start by taking a picture of it. And just like last time, we then binarize the image. We now have to extract the letters so that we can use them later. We do this by performing several actions typical of any computer vision problem. Now, all of these were a giant pain for me when doing my project, since I had to implement all of them from first principles. We start by performing edge detection, where we figure out where one letter starts and another one ends. It's important for us that our letters don't touch, or else we might not accurately be able to tell them apart. Next, we perform contour extraction, where we trace around each letter so that we can extract it out into its own sort of image. Since we know the sentence that our subject wrote, we can also label each of the letters or each of the images, which makes storing and retrieving them much easier. These letters that we've now stored and labeled can now be put together in any order to make any sentence that we want. To make a sentence, we first need to figure out what sentence we want to write. I think let's do "This is my favorite talk." Now you can see why I wanted Candace's handwriting for this. And since this is soon to be Candace's favorite talk, and probably all of yours as well, please remember to scan the little QR code on the back of your things and rate my talk. Each of those letters that we've saved earlier can now be put together to make our sentence. This sentence is great. This is my favorite talk. This is awesome. The sentence generation process that we used sort of caused me some problems during my project. The main problem being that you can't just place letters next to each other. Instead, some letters need to be shifted vertically, either up or down, to match with the rest of the letters in the sentence. To solve this problem in a dynamic way that would hopefully work for each person's unique handwriting, I grouped letters into 3 different categories. They are risers, fallers, and neutrals. I know, very scientific, but bear with me. It's the sort of classification that only a true genius or someone with a fondness for complex oversimplification would come up with. Now, before we proceed, let me preface this with a quick disclaimer. I am not exactly a font expert, so while I am here to explain some font-related concepts, please do not expect any beautifully crafted typefaces. My handwriting is already legendary for all the wrong reasons, and let's just say my font knowledge is about the same. So, if you were expecting a masterclass in typography, I'm going to need you to adjust your expectations down. All the way down, way down. Even further down. Okay, let's go. First up, we have risers. These are all the letters that go up. Think F, L, D, B. All capital letters are also automatically risers. Next, we have fallers. These are all the letters that go down. Think P, Q, J. And lastly, we have neutrals. These are all the letters that don't go up or down. Think A, O, U, R. Basically, if it's not a riser or a faller, it's a neutral. Along with grouping the letters, I also used a special 3-line system to go along with it. When making a sentence, imagine that there are 3 lines in a row. Neutrals get placed with their middles on the middle line. This is because most neutrals sort of align nicely with each other as we write. Risers get placed with their bottoms against the bottom line so that they can align nicely while their tops sort of float. And fallers get placed with their tops against the top line so that their bottoms can dangle below the rest of the letters. This three-line system isn't perfect, and I still have sleepless nights over how I can possibly improve it, but it does, however, work for most people's handwriting. It does sort of give problems on handwriting that's super big or super small, but on average, it's okay. Putting all of these new rules into place, categorizing the letters using the three-line system, we end up with a sentence that looks like this. But sadly, we can't write it just yet. You see, looking at this image, it looks normal. We see lines. Now, to our eyes, they're just lines. But for a computer, these lines are a whole bunch of pixels all placed next to each other, which give the lines width. Now, for us, this is a problem. From what we've discussed earlier, we know that the system is going to try to draw or write on each black pixel. Now, this is a problem since the lines we want the system to draw have width. We're going to find that it needlessly writes lines wider as it tries to fill in this width. To solve this problem, we need to make sure that each line is only 1 pixel wide. That way, the robot goes up and down instead of needlessly going sideways. We can achieve this by using what's called a thinning algorithm. Now, I would love to say that I came up with the idea of a thinning algorithm, but no, the algorithm that I used is called the Zhang-Swen thinning algorithm, and I would love to explain to all of you how and why it works, but I'm pretty sure that I need to sell my soul to be able to do that. I was only able to implement it myself because of some very useful online articles that I found. Google and ChatGPT. But nevertheless, we end up with a sentence that looks like this. The same thing, but each line is now only 1 pixel wide. Now we can finally write our sentence. And if you will just give me a second to make sure how to actually get it going. I need to make sure that it has paper, the pen is in, it is turned on, things are spinning. And now, everyone please hold all of your thumbs and the people next to yours, and we hope that soon it starts moving. Let me just lift it up so we can see the things. Aha. So it starts by making a serial connection between the robot and my laptop and calibrating itself to the top left corner of the page. That's because that's where most of our handwriting starts. For those of you in the front row with really good eyesight, you'll see that it sort of writes like we do, where it does most of a letter, but because of that whole looking for the next neighboring pixel thing, there is a chance that it finds a pixel that's closer to what we think it should write, and so it writes like half a letter, and then continues, and then half a letter, and then comes back to finish the letter. So it doesn't exactly do it in the perfect order. And it is almost done. I promise this won't take much longer. Sick, we're done. Let me just take this out so I can prove to you that it did actually do things. It did the thing for those of you with really good eyesight. You are welcome to come look at it afterwards. And just like that, this is now officially Candace's favorite talk. And so for those of you who now it is also your favorite talk, please remember to take your little cards out and on the back just scan so that I could be your favorite talk officially. Or I'll just make up a sentence with your handwriting. Now that we've spoken about this robot, let's get back to first principles. Engineering teaches us the value and necessity of building and designing things from first principles. You need to have a fundamental understanding of how certain things work to build certain systems and work with certain technology. This process, although well-intentioned, without a doubt has its downsides. And it's these downsides which hamper human growth and ingenuity. Cars are the perfect example of this. I love to drive a car, like many do. But how many people do you think fully understand the theory behind the modern combustion engine? Or what about the math required to determine the correct axle thickness to prevent drive shaft breakage due to high torque acceleration? Almost no one. Well, literally no one. I sort of made up that last example. But that's exactly my point. To drive a car, To love driving, I don't need to know these things. Yes, it's important that someone does, but not the end user. This same approach should be taken for technology. I don't need to worry about how Flyway is performing its database migrations on a register level to effectively use it. Having something like OAuth to manage the passwords and login of users abstracts away the extreme complexities of security in that field, something that I am no expert in, but that doesn't stop me from using it and bearing its fruit. I don't want to have to worry about how my compiler is optimizing my for loop that I just made, but nevertheless, I'm using that capability and bearing its fruit. And so, as the creators of tech, and often very complex tech, we need to ensure that we can abstract away as much of the complexity from our users as possible. This includes complexity not only in using our system, but in integrating their systems with ours. All that having this confusing tech exposed to the user does is it creates barriers for entry and barriers for usage. Imagine having to understand angular momentum to be able to get into your car and drive to work in the morning. Throughout our lives, we've already done away with this idea of first principles. From an engineering background, we're taught that everything should be from first principles. But through building this robot, I've learned that the way we work and the way we build is not how we're taught. This robot of ours that we've just spent the last 20-something minutes of our lives building is the perfect example of this. Even in a project where everything needs to be from first principles, there are many aspects that aren't. Imagine how much longer this thing would have taken us to build if we first had to understand the theory behind how stepper motors work, or how to build our own working stepper motor. Do you think we'd be able to achieve the 0.9 degrees accuracy of a commercial motor? Probably not. Even within the robot, as soon as we finished a subsystem, we immediately abstracted away that complexity from ourselves so that it's easier to integrate with the other subsystems later. We started with a pen that needed to move. Once we figured that out, we could forget about all the bearings and rails and motors and just focus on the code for controlling them. Once that was done, all we needed to do was worry about how to get handwriting into the system. Once that was done, all we needed to do was figure out how to make our own sentences. And once that was done, all we needed to do to use the system is take a picture of handwriting, type a sentence, and press a button. This task that previously seemed impossible at the start now boils down to 3 simple steps. If we wanted to expand the system, make it even cooler, and extend its capabilities, all we need to do is build on our previous level of abstraction. If we wanted to make this robot smart, we could just add speech to text, which would replace us having to type the sentence we want. So, what now? Where does this leave us? Should we just do away with the ideas of first principles? Toss them aside like the baby with the bathwater, never to be seen or heard from again until they fade into mystery and become nothing more than a myth like the lost city of Atlantis? Well, no, luckily not quite that extreme. First principles, like many things, are good in moderation. A good servant, but a bad master. They're like marshmallows. 1 or 2 and you're fine, but after a whole bag full, you're left feeling all sticky and gross. First principles should be treated as domain-specific and should only be considered and implemented within their relevant domain. The best way to understand this is through an example. Let's say that I was busy building a library. The library deals with sorting. It sorts arrays, it sorts lists, it can even sort M&Ms. Now, within the domain of me making this library, I would probably need to implement the specific sorting algorithms from first principles. But I wouldn't require my end users, those using the library, to worry about those first principles. They wouldn't need to understand my implementation to use my library. All of us, as creators, as technologists, the complicated technology that we create can be hard to understand, but should be easy to use. The brilliance of innovation lies not in constantly recreating the wheel, but by building on the works of those that came before us. It's about knowing when to dig into the first principles and when to abstract that complexity away so that others can stand on our shoulders and reach even higher. Isaac Newton once said, "If I have seen further than others, it is by standing upon the shoulders of giants." The next time you create something, anything, spend some time thinking about the first principles. They're our foundation, our roots. But remember, roots are only the beginning. It's what grows from them that truly matters. Where would you be if you had to keep reinventing the wheels in your life? And where could you be if you really leaned into innovation and strived to build on the works of those that came before you? In the end, it's not just about the technology that we create. It's about how we use that technology to move forward. And if we do it right, we won't just be making robots that write, we'll be writing the future itself. So, as you leave here today, spend some time thinking about the projects you're a part of, the systems you work with, and the innovations you're driving. Ask yourself, are you being bogged down by this idea and need to constantly understand everything from first principles? Or are you willing to stand on the shoulders of giants and push boundaries further than you thought possible? Innovation isn't about doing it all yourself. It's about collaboration. It's about building on what exists and making it better. It's about recognizing that progress is a collective effort, one that's built on the knowledge and achievements of those that came before us. So let's embrace that. Let's continue to build, to create, to innovate, and to push the boundaries of what's possible. Not by endlessly retracing our steps, but by boldly stepping forward, confident that we're building on a solid foundation. And who knows, maybe one day, the tools and systems that we create will serve as the foundation for the next wave of innovation, inspiring future generations to reach even greater heights. Thank you, and here's to the future that we will build together.